pass to the third speaker, who is Daniel Kuznetsov.
Kuznetsov, yeah.
Okay, who is a visiting student from NS Paris-Saclay. The stage is yours.
So, hello. The objective of my talk is to present a little bit this topic of federated learning and some works which are done here in which share on this topic. I will speak a little bit more about what I'm doing personally, but also mention some other works that I've done by Ziki and Professor Zazwaza. So to understand what federated learning is, you have to start by understanding the difference between federated learning and the centralized learning. So I will start by talking about centralized learning, then I'll talk about federated learning. After this, we'll talk a bit about Shapley value and how I use this notion to evaluate the contribution of each client to this general process of federated learning. And I will conclude. So, what is centralized learning? You all know a bit about this, I imagine, because you came here. So you have a model, you have a big data set, and this model takes an input from this data set and gives an output in the label space, which corresponds to the most probable answer to this input. And you can apply it in lots of different situations. We had some inspiring talks today about this, and yesterday, so nothing new to you. You can just choose one you prefer. Image recognition, XOR prediction, one-to brings, modeling, lots of different stuff. Mathematically, what you're doing is that you're just finding a certain point in a big vector space which minimizes your loss function. To do this, you do just this gradient descent, or in practice, stochastic gradient descent. But what if your data set is not one data set, but several data sets, which do not all have the same data? And these constraints are actually very realistic. It happens in lots of different situations. For example, with some smartphones training, because every client has his own private data, which he doesn't want to share with this huge corporation which trains their keyboards inside of their smartphones. Or with some medical information, some hospitals who get their patients' information, but can't share it with other hospitals because of the privacy reasons, once again. But you want to train a big model which will use all this information to solve some practical problems you want to find an answer. And federated learning is all about this. So federated learning, let me read this definition, is a machine learning setting where multiple clients collaborate in solving a machine learning problem under the condition of a central server which would, without sharing their private data. So a lot of challenges arise in this topic. The most important ones are the robustness. It is about not getting swayed away by some noise in your data and some attacks on your training process. The incentive, you want to be able to train your model in the most efficient way, the most quickly, the most cheap way, with the less communication as possible. The efficiency, okay, sorry, I switched to incentive and efficiency. So the efficiency is what I told, and the incentive is how to make your clients really want to collaborate. How do you make a hospital want to share their data, want to train the model on its side because it costs some resources to this hospital. They always have some minor risks of losing this data and losing the privacy of this data, so we have to want to collaborate on this. So that's the incentive side, and finally the privacy reason. So once again, you don't want the data to leak from your model. And what I will be doing is mostly focused on the first two things, so the robustness and the incentive of federated learning, but I will talk about this a bit later. Mathematically speaking, you can present this in the following way. You're just searching for the solution of one of these two problems, which are actually equivalent. So once again, you want to find a certain point in this huge vector space, which would minimize your loss function. But how does the training process happen in practice? In practice, you have your big server and your plural data sets. And the server will send a common data point to each of this data set. Each of the data sets will train the model locally. So it will obtain new information. It will make this gradient step, as described previously. Then it will send it back to the server. The server will make some computations on this new, slightly improved models, and obtain new next point in this parameter space. And you just do the same thing again and again and again and again. So you iterate your steps and this thing. So one step of this whole process, let's call it a round. But what I will be doing and what I will be talking about is client contribution evaluation. And first of all, I would like to explain why it's useful. I think there is this very nice work by Ziki Wang and Professor Chaussées and Kang Liu, which was done here in the chair. Kang is now a professor at University de Dijon, I think. So the idea of her work is to create a game theory setting which explains why the clients have to do this training, why we're interested in really training their models locally. So at each round, we send to the server the parameters, but we also send the effort they contributed to the training locally on their side. And the reward they get is bigger the more they trained. And this shows that in this context, if you respect a few very reasonable conditions, the reward will go up, but also the efforts of the clients will go up, and your training will be much more efficient, and every client would really want to train a bit more and to work harder for this whole learning process. But the problem is that in practice, you can't just ask the clients to say how much they've worked. You have to see how much they worked, because otherwise everybody will just say, yeah, work really a lot, like, they can lie. And in order to do this, we could consider this utility function, which would be just the accuracy of a model, like a certain task evaluation data set. On the server side, you will just evaluate the accuracy of a model you obtain after your whole training process. And the bigger it is, the better it is, or you can consider minus the loss, once again, first. And you would want to create something, a way of paying back your clients, which would be a function of how they contribute to this whole training process. And you would want it to verify this quite rational, once again, properties. You would want it to be efficient, so you would want the sum of these payoffs to be equal to the total utility function you got. So if all the clients made you lose a certain quantity of your loss function, you want to pay it back to them. You want it to be symmetric, so you don't want two clients who do the same thing to your training process to get paid differently, because this will be kind of unjust. You want the linearity, because it's very practical for the computational side of this payoff function. And you want the null player property, which basically says that if a client doesn't contribute to the training process, you don't pay him. Okay, and actually, there exists a magical thing which is called shapely value, which is defined by this formula. I will talk about it a bit later, which is really characterized by verifying these four properties I just quoted. There is an equivalence between being defined by this formula and verifying the four properties I just talked to you about. Okay, now let's dive a little bit in this scary-looking formula I have on my slide. What it says is that the shapely value is the mean of the marginal contributions of the client's utilities. What is a marginal contribution? Imagine that all your clients enter the training process in a certain order. If your client I arrive at the end, and you have a certain permutation before him, it's really what he brings to the already formed subset or already formed coalition of a client who arrives with training process before the client I. But in practice, you cannot really just compute it with this huge utility function, which would be the whole accuracy of the model, because in your training process, you have lots of different steps. You have a certain chronology, you have a temporality you have to take into account. And what you do in order to do this is that you just look at each round, and for each round, you define a local utility function, which is just local loss during this round, which you denote UT, and you compute this Shapley value for this UT. Once again, computing Shapley value in exact manner is very complicated, because in order to do this, you have to do n factorial of valuations of your utility function. And in order to evaluate your utility function, you basically need to do a forward pass on your whole validation data set. So it's really, really costly. You cannot allow to do this for a big number of clients. So what you try to do is that you try to get some approximations of it. The most usual ways are stochastic approximations, where we would get a so-called epsilon delta approximation. So you try to find an estimate which would be very close to the real Shapley value with a very big probability, which should be very close to 1. And you can do this with lots of different Monte Carlo methods. For example, by the permutation sampling, which is just based by the fact that since it's a mean, it's an expectancy, and you just do some basic Monte Carlo. You can show using some Hovding inequalities and this kind of stuff. You can really determine the time after which it will work. But unfortunately, this time is quite big. So we have another method which works slightly better, which evaluates the difference between two clients, the Shapley values of two different clients for every pair of clients. And from this, using the fact that you know that the Shapley value verifies the utility function, the efficiency function property, sorry. So basically, the sum of the Shapley values equals the total utility. You can, once again, estimate it. This works a little bit better, but unfortunately, I will have a slide on this later. It still takes some time, and you still have to do lots of forward passes to estimate it correctly. So another way of approximating it is to just do a Taylor approximation of your utility function. For example, here we can take the first order approximation. In this case, your utility function will just be defined by the second formula you have here. Once again, it depends on S in ZT plus 1S, because you look at the utility function associated to a subset. So you want the subset to play a role, which happens when you take S in the thing. It's just a subset of which you evaluate the utility. And since Shapley value is linear, you can say that the Shapley value of U is approximately the same thing as the Shapley value of its Taylor approximation. And this will give you this very nice formula, which basically looks like just some reinforcement learning thing. You look how much the vector of a training step you do goes in the same direction as the valuation vector you would have. And if you can also push your Taylor approximation to the second order, the calculation becomes a bit more big, but basically it's the same thing. By doing this, you get some quite precise numerical results. So to compare this, the exact calculation is just impossible in complex terms, but it's exact. You have a permutation sampling, which would be by run big O of n squared log n, which is, once again, impossibly big. You have the group testing, which goes better, but still takes lots of time. And finally, we have Taylor approximation, which in the second order case only allows you 4%, like you get a precision of 4% on your result, which is quite good. And it is much less costly in terms of operations you need to do this. You need to do to calculate this thing. So we conducted a few experiments to see how much you can use this to improve your training results with some noisy data on the first experiment. So here, we just generated half of the clients with some just randomly permuted labels. We looked at what happens. We can see that actually the training process still goes well because you just have some noise and you still have half of clients who have some good data, and this good data is not perturbed by this wrong data. So, but the accuracy of the training is good, but the loss function seems to be much better if you use the shapely data. But another advantage is that it allows you to see which clients are bad, which clients are noisy. And this is this last figure. Each point is a client, and the vertical scale of the figure is just a shapely value. So you can see the groups, the upper one and the downward one. The group up is mostly good, except from this point around, brown point around 10, which is just random mistake. But if you train for a bit longer, I think it's going to go up again. So yeah, unfortunately, it just takes some time. And on the right, you can see the wrong clients, and you can really see the difference between them after the training. So you can use this to evaluate the contribution of the client. But even better, in case of an injection attack, if you put some clients who all say you something wrong, but the same wrong thing, your training will be really disastrous, which you can see with the orange graph at the left side. But if you use the shapely value evaluation and you change the weights of the clients through process to be in accordance with the shapely evaluations, you get a consistent and good result. But once again, in order for it to be incentive, you want the shapely value to motivate the clients to stay in the game. And the core is all about this. The core of the game is the subset of the different ways you can pay your clients so that no coalition of the clients would feel that they're underpaid, would feel that they contribute more than what they're getting paid and would want to leave. And actually, there is a property, which is the convex game property, which your game have to verify in order to shapely value to be in this core of a game. This convex games property is described by this scary-looking formula, once again. But basically, what it means, once again, is that the marginal contributions of your clients to a certain subset would be a function which would go up the bigger the subset is. And by using this property, what we want to do, what we're trying to do, and have some good ideas of how to advance in this direction, is to actually, this convex game property is not verified in practice. Because in practice, your loss function would be something like this, minus loss function will be something like this, and it will be actually concave. So it's really not something which is true in general setting. So what we are trying to do is to find a way of making the shapely value, find the utility function which would make this game convex. And in this way, our shapely value would be useful, and our clients would still want to participate. So, to conclude this whole talk, there is these 4 main problems related to federated learning. The robustness topic is more or less what we discussed. We can use the shapely value to evaluate the contribution of each client and This way we can see which clients are making some bad data and trying to attack you, and you just don't take your data in account and you train your model. The incentive learning can be used using the article I quoted in the beginning of this talk on this game theoretical approach. The efficiency, there is this article once again by Kang, Wang, and Zuazuaza, made here in the chair, on an algorithm which takes the second problem formulation of federated learning I had on one of the slides in the beginning to make a more efficient learning algorithm which would not have some drifts which you usually have in federated learning if you just do some averages of the steps you get from the different clients. And finally, the privacy topic, there's this very nice article about a reconstruction attack in federated learning. So usually you use federated learning because the data is more private. You don't give the data directly, just give the parameters. But this article shows that if you're not training your model on a long time enough, your privacy gets, you can lose some privacy, and an external person can get your data. And this is what is shown on this image. So one client has this image of a dog, and just by seeing the parameters, you're basically doing this kind of gradient descent, in sort, to get to this image of a dog, which is contained inside the client's data. Thank you for your attention, and I would be glad to answer any questions you have.
Thank you very much, Daniel. And are there questions for our last speaker? Okay, I will just have a curiosity. If you have, for example, patients which have rare data in their clinical records, what is the impact of these rare features on federated learning? What kind of impact do they have? Are they undervaluated?
Actually, no. Actually, they're not. I don't believe they're undervaluated because if you look in on the second term of a shapely value, it's basically something which makes rare data more valuable. And if you have a large enough training data set, so relation data set, you will still have this rare data inside of it. And in this case, this data still be somehow seen and still be very useful. But once again, it maybe won't be the usefulness of it still depends on the rareness of it. So maybe if it's very rare data and it only happens to this client, this patient, his data is not really useful for training a global model because it's something which only happened to this client in the whole history of humanity. Well, it doesn't really generalize well. So
yeah, I see.
Maybe it's, it will still have some bonuses on this, but maybe less with some rare, but not too rare patients.
Okay, yeah. Okay. Maybe just last question. Can you comment again on the attack detection? What should we observe on that plot?
On this one?
Yeah.
Okay. So what we observe on the plot is we can see two groups of the clients, two groups of the points, the left one and the right one. And the clients on the right are the attackers, or just some noisy clients. And you can see that the shape evaluation for these clients is small, is even negative for most of them.
Okay.
But for those who really contribute to the learning process, they have some positive shape evaluation, mostly, except the one which got 0, which basically means that he never got called in the training process. So probably he would get a positive evaluation if he used his data.
Okay. Okay, I see better now. Okay. If there are no other questions, I would say we can end the morning session and we can resume here at 2:15 for the afternoon session. Okay, so enjoy your lunch. See you later. And thanks again to our last speaker.